All right, let's suppose that we have a logistic differential equation that models a population development. And it's given to us as dp dt is 0.026p minus 0.00052 p squared. And t is weeks. What is the carrying capacity? So, hooray for vocabulary words. Carrying capacity is the maximum population that it's the horizontal asymptote. So it's what the population will grow to and level off at as t goes to infinity. The simplest method here, you were presented with a standard format for a logistic equation. And it's dy dt is equal to a constant times y times 1 minus y over m. And that capital M is literally the carrying capacity. So one of the simplest things that you could do is manipulate this dE until it looks exactly like that, and then circle your answer. This is what that looks like. I have dp dt. I'm going to factor out 0.026 capital P, and what's inside the parentheses will be 1 minus 0.02p. And what that means, I'm going to do one more little piece of algebra. This is equal to 0.026p times 1 minus p over 50. Bam! 50 is the carrying capacity. But I want to make this remark. In logistic growth models, there are always going to be two equilibrium solutions. And an equilibrium solution is where dp dt is literally equal to 0. And those equilibrium solutions are going to be dp dt, one is going to be p of t equaling 0. All right, if there are 0 critters, there's not going to be any critter growth, right? So dp dt will always be 0, so that makes sense. The other one is p of t equals m. And so what that means is what you can do is solve dp dt equals 0 and choose the non-zero solution. By taking this and setting it equal to 0 and solving, you're going to find the carrying capacity. I'm trying to point that out because this vocabulary word, carrying capacity, only applies to this concept of logistic growth models for populations. But this term, equilibrium solutions, all differential equations can have equilibrium solutions, and carrying capacity is an example of an equilibrium solution.